An algebra of sets A is called a sigma algebra if for any sets A1, A2, and so on in our collection A, the union is also in the collection A. So finite unions of sets in the algebra are automatically in the algebra, but countably many need not to be in the algebra. And I would say that sigma algebra is the main notion for probability theory. In fact, it starts from sigma algebra, and also so Lebesgue measure will be an example of a probabilistic measure. In fact, one of typical examples. So this theory will help you to understand better probability theory. And number theorem is 4. Theorem 4. The algebra of Lebesgue measurable subsets of Ki forms a sigma algebra. So proof. What we have to prove? We have to prove that union of countably many Lebesgue measurable sets is again Lebesgue measurable. And we'll do it firstly. So suppose firstly that AI are disjoint. So we consider disjoint union of AIs. We are talking about disjoint union. Then according to by properties of outer Lebesgue measure, we have outer measure of the union, disjoint union is less or equal than sum of outer measures. And since we know that all of them are Lebesgue measurable, in fact, we have just Lebesgue measures here. But of course, we don't know yet if this set is Lebesgue measurable, this countable union of Lebesgue sets. Okay. Also, what we know is that for arbitrary finite M, for arbitrary natural M, we have union is a subset of Ki. Hence, by finite additivity of the Lebesgue measure, we have the following inequality that the sum of measures, which is precisely measure of this finite union, is less or equal than measure of ki, that is 1. So since this is valid for arbitrary m natural, we have also that the sum of this series is less or equal than 1. In particular, it means that this series converges. And if we have a convergent series, then remainders tend to 0. So for arbitrary epsilon greater than 0, we can find, let's say, R natural such that the sum from R plus 1 up to infinity of measures of AI is less than, let's say, epsilon over 2. Yeah. So that is because of the convergence of this series. The series is convergent, hence the following inequality holds. So then again, like we did, it follows that the outer measure of the union from R plus 1 up to infinity of AI is also less than epsilon over 2. Okay, less or equal maybe. No, but strictly less, because definitely we have strictly less than that one, and hence, less or equal than that one, and that is strictly less than epsilon over 2. Okay, then consider disjoint union of the first R sets AI. Since, as we know, Lebesgue measurable subsets form an algebra, finite union is Lebesgue measurable. It is Lebesgue measurable. Hence, by theorem 1, that is criteria of measurability, by criteria, again for arbitrary epsilon, okay, I'll fix that epsilon. So we can find there exists elementary set, let's say M epsilon, elementary, such that outer measure of this disjoint union symmetric difference with M epsilon is less than epsilon over 2. So that is measurable. In fact, here I can omit this star because we know this set is Lebesgue measurable, but it doesn't matter. In theorem, we had outer measure. Okay, so then we want to prove that the infinite union is again Lebesgue measurable, and this will be proved by, again, by theorem 1. so by measurability criteria. And how we'll do it? So now let us estimate the difference, disjoint difference, symmetric difference between disjoint union of AIs and our set M epsilon. So consider that one. Consider that one. Consider that one now, right? Then what we have? This symmetric difference, by definition of symmetric difference, that is what? Okay. Maybe I'll write inclusion. Inclusion. So look, symmetric difference is difference from that. We should subtract that one. And I'll split it into two parts. So firstly, difference from the union of the first R minus M epsilon. Then the union of the rest. So you see, what is written here is something what covers that difference. Why? Because here we should consider elements of this disjoint union without M epsilon, right? What we consider here, elements of this union without M epsilon, and elements of that one without extra restriction. So I omit here restriction minus M epsilon. Then of course it will be larger, right? If instead of difference I consider without difference, because difference is smaller than the set without difference, right? Yeah. Okay, that is with this difference. And also opposite one. And for the opposite one, so what I should consider? I should consider minus disjoint union of all, right? But what is minus disjoint union of all? So I should consider elements of M epsilon which do not belong to each of those, right? And I'll replace it by the union of the first R. Then of course, once again, this difference is larger than difference when I put here infinity. Because we delete, here we delete less elements than when we put here infinity, right? So, and that is what is it? That is precisely if we unify those two, once again, look, so I should consider in both cases minus M epsilon, right? In both cases. But here I omit it, and this set will be larger. So I increase the set. And also here, when I delete finite union, it means I delete less than when I delete infinite union. So once again, this set is larger than when I put here infinity. So I enlarge here a little bit, enlarge, yeah? And then you see why I did it. Because now, if we look at the first and the last together, then we obtain the disjoint difference. Sorry, symmetric difference. Symmetric difference. Symmetric difference. Yeah. So that is the first two, and the middle will be the last. Yeah. Okay. After that, look. Outer measure of the first less than epsilon over 2, right? Outer measure of the second is also less than epsilon over 2. We have, because of those two inequalities, right? We obtain that. So all those inequalities imply that outer measure of this symmetric difference is less than epsilon. And what it means? Since epsilon was arbitrary, so we found an elementary set such that this outer measure of the symmetric difference is less than epsilon. Hence, by theorem 1, once again, criteria of measurability, we obtain what we wanted to prove. What we want to prove, right? Yeah. So, theorem is proved. So once again, the example of Lebesgue measurable sets is one of main examples of sigma algebras. And in probability theory, sigma algebra is one of main objects. So you will start with it practically. Okay, then next theorem, theorem 5, that is simultaneously definition of, so its name is definition of what is the name. Sigma additivity of the Lebesgue measure. If A1, so on, up to infinity, are disjoint Lebesgue measurable subsets of Ki, then the Lebesgue measure of the union, disjoint union, by the way, I forget to finish the proof, is equal to the sum of measures. Sorry, now I remember that I forget to finish the proof. Sorry. Yeah, you see. Firstly, we supposed that AI are disjoint, right? So we proved for disjoint, but not for general case, right? So general case, just this is enough. General case. So put A1 tilde equals to A1. And for all others, AI tilde equals to AI without union of former AJs. Then you see, then the union of AIs is obviously disjoint union of AIs tilde. Why? Because what do we consider here? we forget about intersections. That's all. So if there are intersections, then we take them into account in the first occurrence. So first time when we meet some element, we keep it in that set, and when we meet second time, we do not include it into that one. So, and that's all, right? Because if all those sets are Lebesgue measurable, then AI tilde is Lebesgue measurable, then we have disjoint union, and by the first part, it's Lebesgue measurable. That's all. Okay. Then now general case is also proved. Okay, so let's return to that sigma additivity. So let me say a few words about this property, sigma additivity. So in fact, standard definition of measure, not Lebesgue measure, are just arbitrary measure. So what means measure? Measure means a function which is defined on some sigma algebra of sets, and values should be non-negative for every set in this sigma algebra, and it should be sigma additive. So according to that definition of general measure, Jordan measure is not a measure. That is why you can find many textbooks where it is written, it is called, for example, Jordan content, to avoid the word measure, because measure is always sigma additive. According to general theory of measure, measure should be sigma additive. And in probability theory, so I would say standard probability theory starts with what? You have probability space. What is probability space? A set, like here we had Ki, right? Sigma algebra of sets, subsets of this set, and sigma additive measure, such that measure of the whole set should be 1, like in our case. So that is typical example of probability measure. So what I did, several lectures I gave to you, prove that Lebesgue measure is an example of probability measure, but attention, please. Probability measure, it should be 1 for the largest set. That is why also I choose Ki to be unit, so unit cube, right? And of course, later we'll generalize Lebesgue measure for arbitrary space and for not for a small cube, but just for the whole space, right? And it will be not a probability measure anymore. But nevertheless, you see, yeah, I hope it will help you in future with probability theory. Did you start probability theory? Not yet? Not yet, yeah. So you see, of course, usually Lebesgue measure is not covered in calculus, but in probability theory, they do some, I don't know, in fact, usually they go very quickly without detailed proofs and so on. So I decided, because of extra time which was given in this semester, so I decided to present in more details the theory of Lebesgue measure. Okay. Okay. So proof. Proof is essentially simpler than finite. additivity, in fact. So, proof. Look, so what we know that union of AI, finite union, is a subset of the infinite union, right? It's obvious, right? Both are Lebesgue measurable. Hence, we have that measure of the union, of finite union, which is in fact by finite additivity, is finite sum of the measures, is less or equal than measure of the infinite union, right? This is valid for arbitrary m. This is valid for arbitrary m. Hence, that is for arbitrary m. Hence, we obtain the inequality that the sum of measures of AI is less or equal than measure of the infinite union. Measure of the infinite union. Okay. Okay. Now, for the opposite inequality, opposite inequality just refer to property of outer measure, property of outer Lebesgue measure. So, if we denote A as this infinite union, right? Then A is covered by this infinite union. In fact, of course, we have equality here, right? In fact, we have equality here. But A is covered, and I refer to property of the outer Lebesgue measure. So if we have a set which is covered by countably many of sets, then outer measure less or equal than the sum of outer measures. That is valid for arbitrary sets. Doesn't matter, measurable or not. But now what we know A is measurable, star may be omitted. AI are measurable, star may be omitted. And we have opposite inequality, right? Hence, we have equality. Hence, we have equality. Okay. Now, next topic which I would like to consider is related to continuity property of the Lebesgue measure. Once again, this property is not true for Jordan measure. What is about continuity? So once again, look, Lebesgue measure is a function of sets, right? So if we have measurable set, then Lebesgue measure is a function of that set. And so for continuity, we should define the notion of the limit. Okay, I'll refer to this sigma additivity property. I don't need any more else. So And let me recall some definitions from the first semester, namely limit superior. Limit superior and limit inferior. Limit superior, lim like that, or lim sup. One of definitions was as follows: lim sup of k greater or equal to n x. I don't remember. Maybe let me write like that: xn plus 1, and so on, like that. I don't remember if we start from xn or xn plus 1. Really, I don't remember, but it doesn't matter. It's the same. So, and also analogously was defined limit inferior. Lim inf, that is limit of infimums of those sets. Okay, so these are notions from the first semester for sequences of numbers. Now, I want to analyze that and to try to understand how we can define similar things for sequences of sets. So let me give definition. So definition: supremum of a sequence of sets is by definition the union and infimum of a sequence of sets is once again by definition the intersection. Okay. Then let us think about some particular cases when it is very natural to define a limit of a sequence of sets. So, first particular case. A1 is a subset of A2, so on. So we have an increasing sequence of sets. Then, what is the limit of this sequence? Natural definition: limit of the sequence of those sets. Okay, let me use M because now we are in Rn. Is by definition union. And as we saw, that is supremum, right? By definition. So that is one particular case when it is natural to define limit. Another particular case is decreasing sequence of sets, embedded. If they are embedded to each other, then what is limit? Intersection. Yeah. So the limit is defined to be the intersection, which is infimum, as we saw. Now we can define limit inferior and limit superior. So limit inferior of an arbitrary sequence of sets. So now you see, we consider arbitrary sequence of sets. Arbitrary sequence of sets. What is the limit superior? That is, by definition, look at this. Let us think. So supremum of am plus 1, so on. So that is union, k starts from m up to infinity of a k's, right? So what happens if m increases? Look, so here we consider union of all sets am plus 1, and so on, right? If m increases, then we forget about that, for example, right? So we consider union of smaller amount of sets, right? Hence it may be smaller, right? So it means that this sequence, let me denote it by bm, right? So we have b1, b2, and so on, right? So we have an increasing, decreasing sequence of sets, right? And for decreasing sequence of sets, we know what is limit, right? So it means that I can write absolutely like for numbers. So for numbers, we wrote lim sup, right? Now I can define it once again as lim of supremum am plus 1. So now this definition is correct, right? Because this sequence of supremums is decreasing. Hence, the limit is defined. In fact, that is intersection, right? So in details, that is nothing else but intersection of unions so limit superior of a sequence of sets, which was defined like that. So what is it? How we can describe it in words? What it consists of? So it includes elements which belong to infinitely many of ak. Okay, so once you have an element which belongs simultaneously to an infinite sequence, then it belongs to this limit superior. Yeah? Yeah. Okay. Now everything is done with limit superior. Now limit inferior. For limit inferior, analogously, look at infimum, which is by the definition the intersection, and denote it by, let's say, cm, right? Then what we have? If we increase m, that it means that we intersect small amount of sets, right? It means the set will be larger because we don't need to intersect with am, right? So we have now inclusions like that, right? So we have increasing sequence of sets, and it means we can define now, that is a continuation of this definition, limit inferior, which is limit of infimums, same sequence of sets. And if we remember what is infimum, infimum is intersection, right? And for increasing sequence of sets, limit is union, right? Then here I should write union of intersections. Once again, what is inverse? So if something belongs to this set, it means it belongs to all sets AK starting from a number, right? Yeah. So you see, limit superior elements belong to this infinite subsequence, right? And for limit inferior, it belongs to all sets starting from a number, right? And finally, the last part of this definition, very long definition, right? So if limit inferior equals to limit superior, then there exists limit, simply limit, right? Which is equal to that one, the common value. That is the definition of the limit of a sequence of sets, right? So if those limit inferior and limit superior coincide, then we call it limit. So this definition of the limit includes also those, right? These are particular cases. Okay, now we have a definition of limit of a sequence of sets, and I can give the theorem, Theorem 6, Theorem 6, continuity of the Lebesgue measure. So if AI is a convergent sequence, a convergent sequence of Lebesgue measurable subsets of Ki, then the limit is Lebesgue measurable, and measure of this limit is equal to the limit of measure. Of measures. So it means in particular that the limit on the right hand side exists. So that is continuity, right? We see. What is continuity? You interchange limit and the function. That's it. Proof. Proof is not difficult, but it is rather long because of, it is more convenient to split it into several lemmas. So, lemma 1. Lemma 1. We start with particular cases, those particular cases. Yeah. So, if A1, so on, AI are Lebesgue measurable, measurable, then mu of limit, okay, I tends to infinity of ai's equals to the limit. Proof. So, like in the proof of sigma algebra, that Lebesgue Lebesgue measurable sets form a sigma algebra, put a tilde to be a m without union of former ai's. And of course, yeah, a1 tilde, let it be just a1. So here m greater or equal than 2. Then the limit as m goes to infinity of am's, by definition of the limit, that is union, right? As we saw, that is disjoint union of am tilde, and okay, then what we have? So hence this limit is Lebesgue measurable for sure, because as we know, the union of countably many Lebesgue measurable sets is Lebesgue measurable. But also look at this sigma additivity. So by sigma additivity, by theorem 5, which is still on the blackboard, right? By sigma additivity, what we have? Measure of the limit is equal to the sum of measures of am tilde. Now, what is about those measures? Let me look at the yeah, in fact, why I wrote union? Yeah, in fact, for our case, look, yeah, I wrote like in the proof of sigma additivity, but observe that what is union of ai's? Because of these inclusions, right? The union is precisely am minus 1, right? Am minus 1. So it means that, yeah, yeah, it means that measure of am tilde, how we may represent it? There is measure of AM minus measure of AM minus 1. Look, it's easier to understand by a picture. So A1, AM, minus 1, AM, right? So what is AM tilde? AM tilde is that one, right? So AM, which is not in AM minus 1. And what is measure of this? It is measure of AM minus measure of AM minus 1, right? That is what is written here. But this is telescoping series, right? Look how it looks like. Okay, so I should also denote by A not tilde, let it be empty set, right? Otherwise, for m equals to 1, we have a problem, right? Yeah. Then what we have? M equals to 1. Mu of A1 minus mu of A0 plus mu of A2 minus mu of A1 plus so on, right? So what we obtain then as a sum of this telescoping series? So if you consider partial sum, right? Then what is partial sum? Is mu of the very last, right? And the sum of the series is limit of partial sums, right? So we have precisely limit of mu of AM. That's it, right? Okay, lemma is proved. Lemma 2, analogously, but for decreasing sequence. So if Ki contains A1, contains A2, so on, are Lebesgue measurable, then the limit, measure of the limit equals to limit of measures. Let me change letters, otherwise, yeah. Because I'll refer to lemma 1. And it's more convenient. So let it be B. B1, so on, B2, so on. Lebesgue measurements. So proof. Put A1 by definition Ki minus B1 and so on. So AM is Ki minus BM. Then what we have? Then A1 is a subset of A2 and so on, right? And also all of them are subsets of Ki and all of them are Lebesgue measurable. Hence by lemma 1 says that measure of the limit AM equals to limit of the measures. Now, what is the limit of AM? Limit of AM is union. That is union of complements of BMs, and that is complement of the intersection. Remember, union of complements is complement of the intersection, right? That is elementary property of sets, right? So that is what? Intersection is the limit, right? So Ki minus limit of BMs, right? Then what we obtain? Okay, first of all, of course, limit is Lebesgue measurable, right? Because it's difference that is Lebesgue measurable. And also measure of this limit is equal to 1 minus measure of the limit of BMs. Right? And of course, for every M, we have what is measure of AM. Measure of AM, 1 minus measure of BM, right? So what Lem1 says? Lem1 says that is equal to limit of measure of AM 1 minus measure of BM. And then this inequality gives what we want, right? 1 minus measure of limit equals to limit of 1 minus measures. Then we have the desired result. Lemma 3 Lemma 3 if A1 so on so on are Lebesgue measurable subsets of Ki, then limit superior of AM is Lebesgue measurable. And its measure is greater or equal than limit superior of the sequence of measures. We have no equality now, only inequality. Okay. So look, measurability follows from the definition. So limit superior was defined as intersection of unions, right? Countably many measurable sets form measurable, Lebesgue measurable, and of course, countably many intersected also Lebesgue measurable, right? So that is well defined. Now look. By maybe I erased just yeah. So denote by Bm is supremum of those am plus 1, so on, right? We know that is, as we know, that is a decreasing sequence, right? Hence, by lemma 2, right? By lemma 2, what we have? Measure of limit superior of AM is nothing else by definition as measure of the limit of the sequence of Bm, right? By lemma 2, that is by lemma 2. Lemma 2 is here, right? I can put limit here. Yeah. Lemma 2 is here. Yeah, by lemma 2. Measure, right? Let me write what is written here. So limit as m tends to infinity, measure of supremum is union, k from m up to infinity, a case. So now I claim that is greater or equal than limit superior. And what is limit superior? Lim sup, right? So let me write lim of supremums, measure AM, and so on, right? That is limit superior. Why that is true? Let us think. Because look, measure of this union is obviously greater or equal than measure of each of them, right? So measure of this set is greater or equal than any of those numbers, right? Hence, this measure is greater or equal than supremum. Hence, this inequality. That's it. And that's it, right? Lemma is proved. Okay. And last, okay, lemma 2 was used. Last lemma, lemma 4. Lemma 4. Lemma 4. And then, lemma 4. It's similar to lemma 3, of course, right? So if A1 so on are Lebesgue measurable subsets of Ki, then so how it was written there, so limit inferior is Lebesgue measurable. And measure of this limit inferior is less or equal than limit inferior of measures. Proof. Okay, just by, so limit inferior by the definition is how it was the, okay, I'll use maybe it's easier to do it by taking complements. How I did it? No, I did it just by the definition. So by the definition, so union of the intersections by the definitions, right? So once again, if we denote CM by those intersections, a case, right? Then we have C1 is a subset of C2 and so on. And we can apply lemma 1, which implies like, so practically like we did it before, right? So measure of the limit inferior, right, is equal to measure of the limit of the sequence of set CMs, that is limit of the measures. These are measures of intersections. Yeah. And lastly, what we need to observe, once again, look, what is this limit inferior, which is in the right hand side? Limit inferior is limit of infimums, right? Measure AM and so on. And now you see, infimum is it's correct. Oh yeah. So look, measure of the intersection, right, is less or equal than measure of each of those sets. So measure of intersection is less or equal of each of elements, hence it is less or equal than infimum. Hence we have inequality between these. Lemma is proved. Now I can finish the proof of the theorem just in one line. So it uses lemmas 3 and 4. So let me start with now proof of theorem 6. Look, I'll start with limit inferior, no, limit superior, sorry, of the sequence of sets measures, right? Look, so by lemma 3 less or equal, lemma 3, measure of the limit superior, right? Then limit superior coincides with limit inferior because we have convergent sequence, right? What is convergent sequence? Limit inferior coincides with limit superior, right? So I write here equals to measure of, okay, measure of limit without any lines, measure of limit inferior, which is less or equal by lemma 4, right? Less or equal than limit inferior of the sequence of mu of m. And as we know, for arbitrary sequence of numbers, limit inferior is less or equal than limit superior. Right? Now look at this chain of inequalities. The very last equals to the very first, right? Hence, we have equality everywhere. In particular, limit superior coincides with limit inferior. Hence, there exists a limit which coincides with this. Theorem is proved. Theorem is proved. Okay, and now 5 minutes just to give general definition. So let me give definition. Yeah. We have distant class next week. Yeah. At least I wrote to people responsible and they said that I'll continue to give lectures from this class again. Yeah. But okay, it will be not a job, just for fun, right? Because officially we have non-working days, right? But somehow you should study distantly. Okay, so definition. Since volume is translation invariant, we can call a set A to be Lebesgue or Jordan measurable if all sets A, let's say M vector, which are by definition A intersected with Ki shifted to M equals m1 so on mn integer and integer numbers, right, are Lebesgue or Jordan measurable and put measure of A, maybe Jordan, equals by definition to the sum of measures maybe Jordan, right? And usually for Jordan measure, only bounded sets are considered. So you see that this definition is given for unbounded sets in general, right? But usually when we talk about Jordan measurability, then we consider only bounded sets from the beginning, right? And let me give a picture. So what we do, look, we have this fixed cube, okay, for a plane that is a square, right? We have this square, right? And we shift it. So since volume is translation invariant, then we can, roughly speaking, translate everything into any direction, right? So we know what means to be measurable subsets of this cube. Hence, we can translate the theory to any of those cubes, right? And then what we do, if we consider a set, right? We look at each part. If all of them are measurable, then the whole set is measurable. And measure is equal to the sum of those measures of those portions, right? Okay, I have to stop now. Thanks for your attention.